So the CDF method find the CDF of y. This is most general. Remember, we've said several times that the CDF is certainly more general than the PDF, right? It exists for any random variable, discrete or continuous. It's just that analytically it's not convenient, but maths doesn't care about analytical convenience, right? It cares only about what can be written eventually. So, or how well behaved is it. So, this is always a very well behaved function of the argument and bounded between 0 and 1 and so on, and always exists no matter what y you are looking at. So, for all of these reasons all textbooks always start with the CDF of y. So, that actually turns out, I mean, even though okay, so let us say illustrate it with some example graphically rather than so basically I want to find the probability that y is less than some number y for all y in omega y. So, here we are going to assume that this omega y is a continuous interval, right, and not discrete. As I said, if you have discrete to discrete, you are only looking at PMS, so that is completely outside the purview of this discussion, right. We are not going to use CDF for that again. We are going to use CDF as a general tool, right, which turns out is going to only way to handle this flat, right, the example of the flat G. The CDF does not care what kind of G you have essentially, right. Works for any G, any Fx or Fx. So, it does not matter how I write the input specification, I can write it as a CDF, I can write it as a PDF, if a PDF is is possible, G can be anything, flat, whatever, the CDF can always be written. So, for example, you take that right, if you take this flat take this simple example. Let us say this is my omega x. So, that now omega y, what is supposing, so what is omega y? First thing as I said always is to find this. What is that in this particular example? Omega y is clearly you see you go up and down this way and see what interval you are going here. Obviously, you are going only, right. Supposing it is x1 to x2, this x1 x2 is not the same as this x1 x2. So, please excuse the reusing of x1 x2, right, keep this separate from this. So, if this goes from x1 to x2, but x1 is less than 0, let us say, or no, it does not matter, okay, let us say x1 is less than 0 just for the sake of argument, right. So, and if this is g of, okay, this is let us say y equal to x again, right, I am taking the simplest case of the half wave rectifier as it's found, as it's called here, right. So, remember there are no diodes and no cut in voltages and all, right, half wave rectifier is ideal, it's 0 for, right, less than 0 and right, it gives you the same value for x greater than 0, right. So, this is the point y equal to, so if this is x2, this will be x2 here again, right. So, what is omega y? Let us say it is a closed interval 0 to x2. Obviously, 0 now in this case is very much counted, it has to be closed, right. You cannot by any stretch of the imagination write 0 as an open interval in this case, right. So, so what now? So, this is what we want. So, we pick a y here. So, we are assuming x2 is positive. So, for y in the somewhere in between 0 and x2, we are asking for this probability, which is what? This interval only. You can say, well, minus infinity to y, okay, well, we have to qualify. Actually, the CDF has to be specified for all real numbers y. But in this case, by inspection, you can say that if this small y is less than 0, then obviously this becomes an impossible event and it has 0 probability. That I think does not need to be said we don't need to harp on that too much. So we only care about, right, the increase, that is the interesting portion of the CDF always occurs for y only in omega y. If this y becomes more than omega y, then again it saturates at 1, it becomes a certain event, right. So we are only interested in this portion where what? Something interesting is happening in this output CDF. It's not 0 or it's not 1. Okay. So supposing I pick y for 0 less than y less than x2. Supposing I pick some number in this range, which is here, then probability that y is less than equal to y will be the probability that 0 is less than equal to y less than equal to y, right. Isn't it? I pick a number y, the probability of this entire finding y in this whole range, which is the CDF, output CDF, is basically the probability of this closed interval. So this has to be done with care now, because okay, actually not that much care. So what range of x is now going to give me, this range, output range of y? Yes. So now this has to be mapped, this range must be mapped to the interval on, right, the x interval, let me call it x interval, equivalent x interval, right. That is, you map it to the interval which your one interval on the x axis is mapping to another interval on the y axis. So that is what you have to, so you have to find the interval on the x axis which maps, or the region of the x axis which maps to this region that you care about. So this is clearly the region, in this case it is the region x1 to y. So I have to, instead of, in place of, okay, I start with this y, I go down, I obviously get the same y here, and so it is this. And this can be written in terms of the CDF of x, which is why I am saying, so once I have this, right, I do not need this, right, and of course G I have used, I am not right, I am not obviously claiming that this is going to work for, so right, for any G, this all of this happening y here, putting y here, right, this y is only for this particular G. So conservation of probability now, right, this CDF is equal to this. So this can be written, right, this is now nothing but capital Fx of y minus, well, in this case it may only, it is possibly only this, because we are assuming that this actually x1 can be going on to minus infinity also, it does not matter in this case, right, we are right, can be, there is no reason to, in this case, right, you do not have to subtract anything, it is just simply Fx of y. Isn't it? Since we will write here Fx of x1 is 0. Okay, we are assuming, right, that this is the leftmost point of omega x. So, and of course, what is P Fx of, that is, what is P of y equal to 0? This is what? The probability that y is 0 is now the probability, or it is just Fx of what? 0. Note that is a separate point. Right? Vy of 0 is Fx of 0, is it not? So y is no longer purely continuous, y has this finite probability at 0, and therefore the CDF is the only tool we have in this situation. So it turns out for simple cases like this, the CDF, yes, right, can be used, and then of course I do not have to say that for y more, okay, so what is the plot of the output CDF? The plot of the output CDF shows a jump at 0. So again, right, the size of this board is always an issue for me, but have to keep constantly erasing and so on, but does not matter. Okay. So here if I plot Fy versus y, I do not need to look at of course any negative values, right. So if I plot this, it will be up to 0, it is going to be 0, then at 0 it will jump to fx of 0, which we do not know what it is. I am not going to say it is half or anything, I do not know what it is, right, it depends on the statistics of x, jumps to this, and then it linearly increases, does it not? Or no, sorry, it increases, not necessarily linear, it increases according to fx of y, right, up to x2. So it could be some non-linear increase, whatever, up to x2 in this particular case. I am assuming that x is not going to take values bigger than x2, the input random variable x is, right, not going to take values bigger than x2. So therefore at this point itself, what do I get? I get 1. So I get this, I get the jump, right, this is equal to Fy of 0 also, right, the 0, the CDF always includes the right limit by our definition, right. So therefore so this is Fy of 0 will become equal to Fx of 0, capital Fy of 0 becomes equal the same as Fx of 0, so which is some finite quantity in this case. So this is a simple illustration of the CDF technique, which works, as I said, in general. It requires you to have a full specification of the input CDF, right. So input CDF Fx is needs to be specified, and if this input CDF is a pain in the neck to specify for whatever reason, right, the output is also not going to be a pretty CDF to write down. Okay. So what we are going to do is starting today and going into tomorrow is to look at, is there a direct way to write the PDF. So I am going to assume that you can use this if needed in whatever situation you might find yourself in later on in the future, and I am not going to take any more specific examples of this. But basically, right, remember, to do this you need to look at this number is what you need to find. So you have to map this interval to the x interval, the equivalent x interval. So this technique, CDF technique, maps intervals to intervals and finds it, carries over the probability of one in the interval on x to the probability of the equivalent interval in y. That is all you are doing here. Right. The PDF technique, on the other hand, directly goes for the PDF without worrying about the CDF, and it is widely applicable whenever the input is a well behaved continuous random variable and the function g is also a well behaved function, that is whenever these flat portions are not there.